Black holes are the strangest objects in the universe. Born from dying stars, powered by gravity so strong that even light cannot escape, and hidden behind a darkness that nothing can return from. They are not just powerful, they are somewhat impossible. Because the moment we discovered black holes, we also discovered something far more disturbing. They break the rules of the universe, not the soft rules that can be bent or adjusted, the rules that cannot be violated without tearing physics apart. And the most important of those rules is simple. Information cannot be destroyed. Ever. No matter what happens to matter, energy or light, the information inside them must survive. It's the one law the universe doesn't allow to fail. Yet, black holes do something terrifying. They swallow information and never give it back. A star, a planet, an entire cloud of gas. Once it crosses the event horizon, everything about it seems to vanish from reality itself. Mass remains, spin remains, electric charge remains, but the details, the information, the structure that made something what it was, it's gone. And if that is true, then black holes do not just challenge our theories. They destroy the foundation of physics and they rewrite reality. For all the chaos in the cosmos, the universe has one rule that has never been broken. Not by explosions, not by nuclear reactions, not by the death of stars. It does not matter what you burn, crash, freeze, or tear apart. The information inside it must survive. This rule is older than black holes, older than galaxies, older than the idea of space and time expanding around us. It's built into the mathematics of quantum mechanics and the laws that shape reality. The rule says this: information cannot be destroyed. Throw a book into a fire and the book is lost, but the information isn't. It's still there, in the smoke, the ashes, and the heat. It's scrambled, but not erased. Drop a phone into a volcano and the phone disappears, but the information that made it a phone still exists, in the particles and energy that come out. The universe always keeps track. Nothing is ever truly deleted. Everything that exists carries information. The spin of a particle, the temperature of a star, the arrangement of atoms inside the planet. Every detail counts, every detail is stored. This rule is what makes physics work. It allows us to predict the future, it allows us to trace the past. It keeps the universe logical. If information could disappear, then the laws of physics would fall apart. The universe would become unpredictable. Events would not follow causes, reality would stop making sense. And yet, when we look at black holes, we see something that appears impossible. We see an object that doesn't respect this rule, an object that swallows information completely, an object that acts like a cosmic shredder. And this is where the paradox begins. A black hole doesn't behave like anything else in the universe. When something falls toward it, we can still observe it. We can still measure the light, the heat, and the movement. The information is still there. But once it crosses the event horizon, the point of no return, everything changes. The object is gone. Not crushed, not melted, and not broken apart. Just gone. From the outside, all that remains is a simple description. The black hole keeps three things: its mass, its spin, its electric charge. That's it. No details, no structure, and no record of what fell in. A black hole that has swallowed a star looks exactly the same as a black hole that swallowed a planet, a spacecraft, or a cloud of dust. This is the heart of the problem. If the universe truly keeps all information, then the inside of a black hole should store it. It should be hidden somewhere behind the horizon. But our equations say something different. They say the information is erased, wiped clean, destroyed in a way that should never happen. For decades, physicists tried to ignore this. They assumed there would eventually be a solution. Some hidden mechanism or some deeper rule. But every calculation led to the same impossible result. A black hole doesn't save information. It erases it. And if this is true, the universe is breaking its own laws. This is why the information paradox is not just a puzzle, it's kind of a crisis. Because if black holes can destroy information, then physics does not work. Reality doesn't follow rules. The universe itself becomes unpredictable. And this is only the beginning of the problem. For a long time, physicists believed black holes were eternal, dark, silent, and unchanging. They thought a black hole would sit in space forever, swallowing anything unlucky enough to fall near it. Then Stephen Hawking proved everyone wrong. He discovered that black holes are not perfectly black. They glow, they release energy, they slowly leak radiation into space. This process is now called Hawking radiation, and it changes everything. Here is how it works. Quantum fluctuations near the event horizon create pairs of particles. One falls in, the other one escapes. To an outside observer, it looks like the black hole is emitting energy. Over time, the black hole loses mass. It shrinks, it gets weaker, and eventually it disappears. This is where the real nightmare begins. Imagine a black hole that swallowed a star. That star carried information. Every atom, every particle, every detail. But when the black hole evaporates, all that comes out is random radiation, random heat, random particles. There is no trace of what fell in, no record of a star, no memory of the information it carried. It's as if the universe deleted a file and emptied the trash. The details are gone forever. Hawking radiation does not carry information out. It carries noise, meaningless energy, a final whisper from a dying black hole that says nothing about what created it. This makes the paradox even worse. It means black holes do not just hide information, they erase it. And when they vanish, the information vanishes with them. If this is true, the universe has broken its own rule. Information has been destroyed, and physics has fallen apart. Yet Hawking himself didn't believe the universe could be that careless. He thought there had to be a deeper answer, and to find it, we must go to the edge of the black hole itself. This is the event horizon. It's the most dangerous line in the universe. It's not a physical surface, and it's not wall you can touch. It's simply a place where escape becomes impossible. Cross it, and you're gone. Fall toward it, and the laws of physics begin to twist. From the outside, the event horizon looks calm, silent, perfectly smooth. There is nothing dramatic, no flashing lights, no warning sign. If you drift toward it, nothing special happens at first. Your ship stays intact, your clock ticks normally, your senses feel the same. But that is only your perspective. For an outside observer, everything changes. As you approach the event horizon, you slow down. Your movement freezes. Your light stretches into darkness. Your final moments play out endlessly like a scene paused on screen. Two viewpoints, two realities, both correct but both impossible to combine. This is where physics begin to fail. Relativity says the event horizon is harmless. A traveler can cross it without noticing anything strange. Time continues, space continues, life continues at least for a moment. Quantum mechanics disagrees. It says the event horizon cannot be smooth. It cannot be empty. If information is to survive, something must happen at the horizon. Something violent, something extreme. But the horizon is where information disappears, and the moment information vanishes, the universe breaks its own rule. So, which one is right? Relativity or quantum mechanics? They can't both be correct, but they both describe parts of reality with incredible accuracy. This disagreement is the core of the paradox. A smooth horizon destroys information, a violent horizon saves it but breaks relativity. The universe can't choose both. Some physicists say the horizon must hide a structure we do not understand. Others say the inside of a black hole does not exist in the way we think. And some believe the horizon itself is the key. To explore the next idea, we must imagine something extreme. Something that rewrites the edge of a black hole entirely. If black holes destroy information, physics breaks. If they keep information, relativity breaks. So physicists try to find a middle ground, a way for a black hole to protect information without rewriting the universe. What they came up with shocked everyone. It's called the firewall. The idea says the event horizon is not smooth at all. It's not gentle and it's not harmless. Instead, it's a wall of pure energy, a blazing ring of quantum fire waiting at the edge of black hole. If this is true, anyone falling in would not drift across the horizon peacefully. They would hit the firewall instantly. There is no pain, no slow descent, no moment of silence. You are erased on contact. The firewall burns away everything that falls in, but it doesn't destroy information. It saves it in the radiation. Each burst of heat carries tiny pieces of quantum data like pixels scattered across space. On paper, the firewall works. Information is preserved, the universe stays logical, physics survives another day. But there is a problem, and it's not a small one. Relativity says nothing special should happen at the event horizon. A traveler should pass through without noticing anything unusual. Smooth, quiet, and simple. The firewall destroys that idea completely. It demands that the horizon is violent, explosive, and deadly. The firewall forces physicists to choose between two pillars of science. Both are trusted and both are proven. Both describe the universe perfectly. Yet when we combine them at a black hole, they cannot coexist. This is why the firewall is so controversial. It fixes the paradox, but it breaks reality. It gives us answers, but they come at a price no one wants to pay. And this drove physicists to search for a better idea, one that saves information without tearing physics apart. To find it, we must rethink what a black hole really is. Physicists needed a better idea, something bold, something strange, something that saves information without burning the universe at the edges. That idea became the holographic principle. It says everything inside a black hole is not really inside it. The three-dimensional interior might be an illusion created by information stored on the surface. Not a surface you can touch, but the event horizon itself. A two-dimensional boundary holding every detail about everything that has ever fallen in. Think of it like this. From the outside, a black hole looks simple, just mass, spin and charge. But the event horizon might be covered in microscopic ripples, tiny quantum patterns, a sort of a cosmic code. These patterns could contain all the lost information. A star, a planet, a spacecraft, an atom, a particle. Every detail is recorded on the horizon like data written on a giant cosmic hard drive. The interior we imagine might be a projection, a three-dimensional world generated from that information. Not fake, not imaginary, but encoded in a way we do not yet understand. This idea changes everything. It means black holes are not simple spheres of darkness. They are storage devices, record keepers, archives of everything they have ever consumed. If the holographic principle is right, then information is never destroyed. It's preserved on the surface and slowly released through Hawking radiation in a scrambled but recoverable form. This solves the paradox. Information doesn't vanish. It's smeared across the horizon, released back into space and restored by nature. But it also suggests something even stranger. If black holes work this way, the universe might work this way too. The entire cosmos might be a projection from a distant boundary we can never reach. The black hole information paradox doesn't just challenge black holes, it challenges our understanding of space, time and reality itself. Even with the holographic principle, not everyone was satisfied. Some physicists wanted something more physical, more concrete, something that actually changes what a black hole is, not just how we describe it. So they proposed another idea. They called it quantum hell. For decades, black holes seemed to be simple. No features, no structures, no details. Just smooth, dark spheres defined by three basic numbers: mass, spin, and charge. Everything else was lost forever. That was the old rule. Quantum hair says the old rule is wrong. It suggests black holes are not smooth at all. They are covered in subtle quantum features, tiny fluctuations, tiny patterns, tiny fields that respond to the information that falls in. You can't see them with a telescope. You can't feel them with gravity. But these delicate quantum marks may hold the missing information. A star falls in, the black hole changes. Just a little. Not enough to notice with normal physics, but enough to store the information in a new quantum pattern. This solves the paradox in a different way. Information is not destroyed, it's not hidden behind the horizon, it's not burned in a firewall. It's written onto the black hole itself as a quantum hair. Then there are more radical ideas. Maybe black holes bounce, maybe they connect to new regions of space, maybe the interior tunnels into another universe. Maybe black holes store information in quantum entanglement across distant parts of space. Each of these theories tries to rescue physics. Each tries to make sure the universe doesn't break its most important rule. But the truth is simple. We still don't know how black holes store information. We have pieces, we have clues, we have theories that almost make sense, yet none of them are complete. And that brings us back to the real question. If black holes do not destroy information, then where does it go? For all the theories, calculations, and brilliant attempts to solve this paradox, we are still left with a universe that refuses to reveal its plan. Black holes sit at the crossroads of two great pillars of science. Relativity describes gravity and the structure of space. Quantum mechanics describes the behavior of particles and information. Both are powerful and both are accurate. Both have been tested again and again. But when we bring them together at a black hole, something breaks. Relativity says the event horizon is calm, quantum mechanics says it can't be. Hawking radiation says black holes evaporate, information conservation says they cannot lose anything. The holographic principle says information is on the surface, quantum hair says the black hole itself holds the details. Every idea solves part of the problem and none of them solve the whole thing. And this is the strange part. The information paradox is not about black holes, it's about the universe, because if information can vanish, then physics collapses. Equations stop working, cause and effect fall apart, the future becomes unpredictable. Physicists are not afraid of black holes, they are afraid of breaking the one rule that holds reality together. So why do we still have no answer? Because solving this paradox requires something we do not have. A new theory, a deeper law, a bridge that connects relativity and quantum mechanics into a single picture. A theory of quantum gravity that explains the structure of space and time. That theory doesn't exist yet. We are close, we have clues, we have pieces, but the full picture is still out of reach. Until we uncover it, black holes remain a riddle. A place where physics refuses to choose a side. A place where information seems to disappear and yet somehow must survive. The paradox remains unsolved. Thank you for watching, keep looking up.